So this thumb instruction indicates 16-bit instructions, whereas ARM instructions are also supported, which is the core instruction or main instruction set, which is 32-bit instruction in ARM 7 architecture. And debugger means, debugging is a process to eliminate some problems or bugs in your program. Okay, so this I said that the in-circuit debugger is present inside ARM means if you are if you have written a code for the processor for this processor, for example ARM 7, and then if you find some error in your code, so how do we generally approach? We just read our code and we try to check the logic and the flow of the code, and then that's how we debug our standard software routines or standard software codes. Whereas in embedded system, this in-circuit debugging is very important. In this debugger means it involves hardware and it actually checks how the hardware behaves. And a part of the debugger in the advanced form is called emulation, which is written later on. So you'll see that this in-circuit debugging and in-circuit emulation, they are slightly different, but these are considered to be separate features these days, because debugger is a simple debugger where the hardware is involved, whereas for accessing the hardware you need some interface called emulation interface or trace interface. We'll see that those things in relatively more detail. So in circuit, that means within the circuit, within the chip, you can access different portions of the chip and try to understand what's going wrong in your code sequence. So this is for very very complex code writing where timing and accuracy are very demanding. So in such applications, this in-circuit access, that means you can access your chip while it is running. Let's say the microprocessor or controller is executing a code, and while it is executing in parallel, you can actually enter the chip through some digital lines, separate digital lines, and then try to understand what is going wrong or what is going right inside your microcontroller architecture at every bits and pieces or every point inside the processor. Okay, so that means you can access program counter while the program counter is executing the code. You can access something like your special function registers while those registers are also functioning as per your main code. Okay, so that's the meaning of emulation and debugging. We'll see in more detail as we go along. Then there is a specialized multiplier present inside this ARM7. In fact, this is very ubiquitous these days. That means it is present in almost all ARM processors these days. And it also helps in co-processing application. That means synchronous operation of more than one microcontroller or more than one processor is possible. So that means it actually supports multi-code operation through certain instructions and through its hardware architecture. So that's a very brief meaning of this name, just ARM7 TDMIS microcontroller. Okay, so let's move on to the next slide. So there are several versions of ARM processor like ARM Cortex series, ARM 9 series, ARM 7 series, and so on. So there are different architectures within ARM community or ARM portfolio, and those architectures are all RISC architectures. So if you learn any one of these architectures, let's say we have chosen ARM 7, it is slightly oldish, but it actually helps you to identify what was original in ARM, what are the specialties in ARM, rather than lots of fancy features which are present in very modern versions of ARM processors. Okay, so we'll see that all ARM processors are RISC architectures, and their features, their way of design of internal hardware, those things change. Basically, this company ARM writes a set of hardware description language code. They write some sort of Verilog or VHDL codes, which are indeed very complex, very long, and so on. And they copyrighted that code. That means they secured, they claim that's their own development design kind of thing. Okay, so everything is soft development by this ARM, and all the soft processors. So soft processors means you will get a simple Verilog code that is called hardware description language code, or that will be learning or practicing in the VLSI lab digital side. So they develop a very large Verilog or VHDL code, typically Verilog actually, and then they license that code to others. So other people actually get that license or buy that license, like Texas Instruments or even Intel purchase this license, and then they synthesize that code. That means they actually form a transistor equivalent version or the connection diagram netlist for that code. Okay, so this RISC architecture is chosen for all those soft codes, this ARM soft codes, because the RISC architecture provides better timing efficiency at times, and also it offers much more complex operation, although it shows reduced instruction set. So by using a reduced number of instruction set as compared to CISC, complex instruction set, in fact RISC processors can perform even more complex operations if the hardware is supported, if the instructions are also supported. So in my opinion, RISC processors are actually capable of handling more complex tasks as compared to complex instruction set computers. Okay, so this is a misnomer, you can say, where RISC is able to handle things much more efficiently. And I was telling about soft core. So once the company gets those soft core, like Apple, they want to develop A14 chip, for example. So while developing, they will first purchase that soft core from ARM, and then they will do the synthesis in-house, and then they do all sorts of checking or through simulations, as well as later on they fabricate the chip. And once they fabricate chip, we get a ARM microcontroller or ARM processor in hand, which is going to be connected on your device or mobile device. So we discussed that ARM is this 32-bit microprocessor code. It's not a microcontroller. Okay, microcontroller means you need memory and other peripherals. So ARM is just a microprocessor, but we don't use it in microprocessor form in general. We always use ARM chips in microcontroller form. But at the code, at the inside, if you dive inside, it's just a microprocessor code. It doesn't support, or rather, it doesn't say anything how many IO lines will be there, how much memory space will be there. So ARM is only talking about the execution part, like arithmetic logic unit and the parts around that, how to decode, fetch, execute, those kind of things. Okay, and then the ARM features, as I said, two instruction set. You can choose any one of this, and there are reasons why there are two. So we'll see this, see the reasons. So in full featured version, we can have we can execute 32-bit, and then for some other part of the code, let's say we have written a code which can be executed partly in 32-bit and partly in 16-bit. So that's also possible in ARM processor. So there are obvious reasons because 16-bit mode offers better code density, whereas 32-bit mode offers better or higher performance. Okay, so we'll see again how those things are happening through some type of SFRs, special function registers. Then it's a very high performance processor. Obviously, ARM series is a high performance processor, and why it got so popular? So only high performance is not good enough. So you also need to achieve low power consumption. So that's very important. So it consumes relatively lower power as compared to equivalent 32-bit processors from other companies. Okay, so that is why it is very important. It actually breaks the contradiction to some extent. Contradiction means if you have high performance, you should also expect it to be high power because it should consume more energy. But it is actually doing quite a bit of breakthrough to achieve a lower power consumption because we wanted to use ARM for battery power devices. So that is the main reason why low power consumption is important without sacrificing performance significantly. ARM processor uses pipelining strategy to increase the speed or execution rate of the instructions. So there is something called MIPS, M-I-P-S, means millions of instructions per second. So MIPS is a measure of how efficiently your processor is executing code, or that means how many million instructions the processor is able to execute in a given time. So that is basically one of the ways to look at the performance of a processor. And the performance is increased or enhanced by many strategies, and one such strategy is pipelining strategy. Pipelining means parallel strategy. Suppose you have a pipe, a water pipe coming from your tank to your bathroom tap, for example. So what is going to happen? You need to first fill up the tank. That's a separate thing. And after you fill up the tank, the pipe, the inner part of the pipe should be filled up with water all through, right? And whichever part of the, or whatever volume of water that enters the pipe from the tank end should leave your kitchen or bathroom first. So that's the first in, first out. So that's a pipe mechanism, right? So you fill up the water first, whichever part of the volume of water that gets filled up from the tank side will also come out from your bathroom side. So that is pipeline operation, right? It's a first in, first out, technically speaking. So that means how does it increase the performance? The question is. So the performance increase is possible because you have to keep on filling the pipe from the tank end until the entire pipe gets flushed with water inside the pipeline. The entire pipe should be flushed with water. Now, if you keep on doing that, the tank will push more water or throw more water into the pipe, inlet of the pipe, and the outlet will throw out the water continuous basis, right? So that's the standard pipeline in tank analogy. But the point is your entire pipe is filled up with water, right? So in case of processor, the entire pipe or entire sequence or registers are filled up with some or other instruction or data. So that means, so there are lots of parallel things happens due to pipelining. That means one side, the tank end, the water filling is happening, and on the exit end, in your bathroom or kitchen end, water is coming out of that. So that means enter and exit both are happening simultaneously in a pipe in order to make it functional. So similar concept is adopted in processor like this ARM, where data or instruction is fed in one side, and on the other side of the pipe or on the other side of the sequence, the data and code gets executed or information is processed. So things are going in parallel. So I'll say pipelining means this is a parallel operation. Okay, so there is a parallel operation. So parallel operation means either it may be execution of code or data, or actually combination of both. And then there are different stages of pipelining, and such as ARM7 supports pipelining for the instructions. And there are like ARM Cortex higher series like A78 and so on. So they also support multiple pipeline stages, or rather parallel pipeline pathways, where they not just use it for instructions, but also for various channels of data. Like for every memory, there could be separate pipelining in those higher processors. But let's see how this happens in ARM7. So it's a three-stage pipelining means, so the pipeline has three chambers, you can think of it. Okay, so fetch, execute, fetch, decode, and execute. So in 8051, we had seen this execution happens only after decoding, and decoding happens only after fetching of instruction from the memory. So this was a sequential process in 8051. But in ARM, rather it is sequentially right after starting up or after powering up. So first instruction will be fetched, then it will be decoded, then it will be executed. Now the point is, when the first instruction goes into the decode form, the second instruction is actually in the fetch stage. Okay. Okay, and when the first instruction jumps from decode to execute, the second instruction comes into decode and the third instruction now getting fetched. Okay, so this is called a pipelining operation in processors, or three-stage pipelining process, where so all three operations actually happen simultaneously after from the third instruction onwards. For the first two instruction, any one or two are getting involved in this among these three steps, whereas from third instruction onwards, all three things are happening together. That means the third instruction is getting fetched, second instruction in your code which was previous to third goes into decode mode, and then the first instruction goes into execute. And now once the first instruction execution is done, then the second instruction which was fetched, which that comes into execute, then the fourth instruction getting fetched, and the third instruction comes into decode form. It's basically a railway bogie like thing, right? So assume there is a closed railway shed or a platform, and the engine comes first. So engine will enter the shed first, and then it will go further deeper into the shed. Then it will go further deeper. So as the engine actually goes deeper into the shed or under the shed or in the platform, so the subsequent bogies are following just with certain fixed distance or fixed time gap in between. Okay, so that is what a pipelining method is about in general. So you can see this graphical ways, which is one and the same. So we'll see furthermore. So here in ARM7, the program counter PC, which is similar to the program counter that we had seen in 8051. Program counter is a register, 16-bit register that points to the code memory space, the current instruction that should be executed or fetched. So the program counter here points to the instruction being fetched rather than the instruction being executed. So this happens due to pipelining, right? So when whichever instruction is getting fetched, so the fetched location should be pointed by the PC register. Whereas whatever is getting executed, so that is pointed or that is controlled by some other registers or internal state of the microcontroller or processor of the ARM. And this is quite critical and essential because the program counter value is used in an executing instruction is always two instructions ahead of the address. So it means, if you are executing the first instruction, let's say after while the third instruction getting fetched, so that is the PC value. So for the third instruction, and for the second instruction and for the first instruction in the pipelining stage are actually not present in the program counter, and that means the PC value is always ahead or two instructions or two steps ahead of the address. Now, how can we say two instructions? Because in RISC, most of the instructions are typically one word instruction. That means it is either 32-bit or 16-bit instructions. Okay, so it is unlike in 8051. So some instructions were single byte long, such as INCA, and some instructions were 2 bytes long, like AJMP 8-bit address, and some other instructions were 24 bits long or 3 bytes in the memory, so like LJMP 16-bit address. So unlike that CISC-like instructions, RISC instructions are typically having one single word, which is either 32 or 16, and within that you accommodate the opcode, you also accommodate the operand of the instruction. So that is one of the benefits of RISC instruction, why it is faster, because within a given word you can actually merge both your opcode and operand, because you have 32 bits here, right? Unless your data is 32-bit or your operand is 32-bit, you can accommodate everything within one word of 32 bits. Okay, but if your relative address jump location may not be 32-bit or 16-bit, it may be just 8-bit or other lengths. So you can merge such operands within the single line or a single word. So that's why this RISC instructions are quite wide, and that is one of the reasons why these instructions are actually wider. So ARM is a 32-bit processor, that is one thing, and it supports 32-bit instruction. That is another thing. Okay, so 32-bit processor means 32-bit ALU is present, and 32-bit instruction means 32-bit instruction decoder is present. Okay, so these two things are different. Now, data in case of ARM could be either of the three possible possibilities, either 8 bits, 16 bits, or 32 bits. So this data, that means you can have an operand which are either of these three categories. And there are different types of memory cycles. So memory cycle means memory access cycles. Okay, so first of all, at a very rudimentary level, at a very basic level, memory cycles means either read cycle or write cycle. So at a very basic level, so that is one way of looking at memory cycle. But there could be other ways which is present in ARM processor, which are idle cycle. That means you have control over the memory, or memory is connected, but you are not accessing the memory all the time. So that is called idle cycle. And then there could be sequential cycle. That means you can sequentially increase the program counter and go to the next memory location. That is sequential cycle. Also, there could be non-sequential cycle. That means you can actually have a jump between the access addresses from the memory, whether it is data or program memory. You can actually have a non-sequential. That means there could be basically some intermediate steps for accessing memory addresses. And then there is a coprocessor register transfer cycle. So that means there are some special function registers through which you can define a processor to be either a main processor or a coprocessor. That means if you have an ARM microcontroller and you can get more than one microcontrollers and connect them together in a given format, obviously, which is specified in the datasheet, and then you can make some of them as a coprocessor, or you can make the same processor as a main processor. So it actually gets configured through code and with the help of some special function registers. Now, ARM7 supports two instruction sets, as we briefly discussed some time back. So 32-bit ARM instruction set. So that's the name of the instruction set. While it is 32-bit, it is called ARM instructions. And while it is 16-bit, we call this instruction set as thumb instruction set. Okay, so thumb means 16-bit, ARM instruction means 32 bits. In ARM 32-bit instruction, so there is a higher performance mode. That means you can have all 32 bits crunched together or decoded together. You can have 16-bit instructions, which is a thumb instruction, and it is mainly used for code density. Suppose you have 8-bit operand, and this is a reduced instruction set, so you don't have a very large set of instructions numbers. So that means you may not need 2 to the power 16 combination of opcodes, right? So that is not needed here. So, or even 2 to the power 32 is out of question for the opcodes. So it is already called as reduced instruction set. So less number of instructions. Actually, it is not so less, but it is. It was originally very less as compared to CISC, while this concept came up earlier. So in the 16-bit thumb instruction mode, so you can achieve a higher code density. That means you need less memory space to store your code. So that is the meaning of this thing, higher code density. Now, we will look at the processor functional diagram. So let's do that. Before that, let me ask you questions. So do you have any doubt until now? So we just have started. So do you have any early stage questions? Okay. I think I'm sure you'll have lots of questions later on. Let's move on. Again, do not learn or mug up this kind of diagrams. but you should always grasp the idea, the core idea behind such big and complex diagrams. Here I'm showing you the processor functional diagram. So functional diagram means once the ARM company develops a core they develop the soft design, hardware description design. So they actually offer you the interfacing lines. So these are not microcontroller pin configuration. Okay, this is just a functional diagram and showing the interface lines which are present. You don't have to remember all the lines because you are not designing an ARM microcontroller. Rather, we are trying to learn how to use a ARM microcontroller. So if you are taking up a research project on developing a new microcontroller using hardware description around an ARM processor, then you have to go in this kind of details. But I just wanted you to look at whatever is written around those curly brackets. Okay, just look at those groups of lines which are stated or specified here. So the first group is the clock and timing. So that means you must need a clock signal. You cannot avoid a clock signal for any processor in general. You also need to have some interrupts. So ARM7 helps in connecting interrupt sources, and there are different types of interrupt sources that you can see by name at least. So we'll see some of them in detail as we go along. So the interrupt, so this is a generic diagram. So there, look at this. So they are trying to build a house which can be modified for a hospital or for a school or for a residential purpose or for some other industrial purpose. So think of this way. So the ARM company is developing a processor which can be used for any application, whether it is industrial or space or medical or any other application. So or robotic or any just any application. So for having such a generic architecture, they are actually defining what should be the minimum required interfacing connections or how many windows and doors they are going to install. So that kind of information is over here. So from this interrupt, so although you can see there are the only three types of interrupts shown here, but using these three lines or three types of signals, you can have even hundreds of interrupt sources connected externally, and then it boils down to these three lines, which is eventually getting interfaced with the ARM7 TDMI core. Then there are bus controls, so you must have some control of address, data, and control bus. So those three buses should be there, and those bus interfacing lines are unavoidably important. We'll come to debug a little later and the boundary scan. So we'll come to memory interface. Now look at this. There are bus control lines and there are memory interface lines. Okay, so how does it mean? What are the differences between these two types? So bus, as I said, address, data, and control, whereas memory interface will also require address data, right? So here you can see A3120, that means 32-bit address lines, and then data. There are different data lines. Look at this. There are three types of data lines for this: D in, D out, and simple D. All these are 32 bits each. So there are so many lines for memory interfacing, and through this you can actually connect multiple memories simultaneously, such as if you're having a flash ROM or some or non-volatile memory. So during runtime, you just need this D in type of signals, right? Because you are just taking data inside the processor. So you don't need to bother the other buses. Whereas if you need a RAM kind of memory, you can use this D 31 to 0, which is a bidirectional thing. And if you are just writing something to, let's say you are having some memory where you just only want to dump information, but you don't want to read, for example. So in that case, you can use this D out. So these are basically the basic interfacing lines for memory. But in general, the bus control represents not just memory, like ALE and other things could be used for memory as well, but not necessarily always. But this bus control is more generic, which is meant to interface your peripheral devices also. Okay, so peripheral interfacing is also considered in this bus control signals, and some of the lines from bus control may be used for memory purpose as well. But typically, if you need this dedicated memory connected, so only memory interface lines are adequate. Then there are memory management interface. It's basically a type of power management with memory. Suppose if the processor is not reading or writing anything from or to the memory, in such a case, the processor can put the memory in low power mode by means of this different types of signals. And there are obviously power signals, which is the power supply signals. And then we'll come to the coprocessor. So once you have enabled the coprocessor inside, from inside, then there are some data exchange that must happen between the processors, and for that, so there are some handshake lines. So these are basically handshake lines, means basically it's saying that whether are you ready or I'm ready, so and when to transfer data, and through the data bus or memory interface, you can actually transfer the data through in between the co-processors. Now coming to the last few parts, which is boundary scan and debug. So let's look at debug first. Look at this, how many lines they're just spending just for debugging purpose. So debugging is very powerful feature inside ARM processor, and this debugging hardware feature helps in reducing the time for development. Like let's say a company is writing an application compile. Let's say Samsung is making a phone, and for that they have written 2 million lines long code for this ARM processor. Let's assume some hypothetical situation, although it is never possible for this ARM7. For other ARM it is possible. Suppose there is a very long program which has been developed, and now there are some errors which must be fixed. Now, so how do those companies deal with such huge codes around this kind of processors? So there are teams, there are multiple people who actually combine, write different code or parts of the code, they merge together, and then they develop a final big code out of that. Now, if there are some problems inside that big code, so so what is the effect? So that means it is actually misguiding the hardware. Right? If you have some problem in your software that you are developing, it must be doing some wrong steps within the processor, and that is causing some malfunction or hanging operation or some basically undesired sequence of operations. So those undesired sequence is determined if you not just look at your code, but also look at what exactly happens inside the processor at various parts inside the processor, and then if you can read and write to each and every part of the processor, whatever architecture is inside this ARM7, in that case you can actually help to reduce the time for development, or turnout time, or time to market. That is a industry oriented term. Time to market should be reduced as much as possible. And how it is done? You have to look at your code, whatever the developers are doing, and also you have to look at your hardware very carefully. And while doing the hardware, while checking the hardware, it must not disrupt the normal execution sequence like memory interface and other stuff. So while interfacing or reading the hardware, you must have a copy. It's like a Xerox copy of every register, every block inside the processor should be controlled, or should be read actually by this debugging unit. Now there is something called boundary scan, which is slightly different than debug but pretty similar to debug. Okay, so this boundary scan is actually more specialized version of debugging interface, and now they have kept both because both of them are having its own unique applications. For example, the boundary scan means it actually keeps a watchdog. Suppose you have a land, or you have a space where you are staying, your house, wherever it has been built, and there are lots of cameras installed all around your premises boundary, for example. So what are those cameras going to do? They are going to watch every corner of the premises, who is entering, who is leaving, what people are doing inside the premises. Every details should be monitored. Okay, so if you install so many cameras around the premises boundary, similar thing in ARM. So there is a parallel registers. Basically, there are parallel Xerox copies of or photocopies of the each and every values, each and every location, each and every register, each and every block inside the microprocessor gets copied. So in debug, we just can read and write to some every location, but through boundary scan, we are just copying everything. So you cannot basically write directly unless it is done along with debug. So you can just make a copy of everything and bring that huge set of data. Let's say you have installed 100 cameras or on your premises, and then those 100 cameras video data is a very large set of data, right? So such a large set of data from all the registers, obviously in this case it is registers and all the blocks, so which are actually scanned through. That means you actually get a copying, or you're scanning up all the value. That means you're copying all the values from every corner of the chip, which was not at all possible in 8051 like microcontrollers. Okay. And then in addition, for this boundary scan to happen, so there are some supporting signals like the control signals for boundary scan are also there, which is actually happening in conjunction with this boundary scan logic. And another reason why this boundary scan is there, because this lines, basically this T means test, clock, mode select, data input, data output, reset. So these are basically different test signals or they are different test clock signals, which are used to program a memory. Suppose I wanted to, I've purchased a flash version of ARM7 microcontroller. So there is a flash memory connected through the memory interface. Now, after writing a code through your Arduino interface or Raspberry Pi interface or any other integrated development software or environment like Keel or IAR, you wanted to program the memory. Suppose you have written a code, you want to download the code to the memory. So for downloading these boundary scan signals, some of them are very, very important. In fact, they are also available as an external pin, not just from the processor, but also external pin from the overall microcontroller. So by using some of these lines from the boundary scan category, you can not just look at and sniff through your processor registers and blocks, but also can program your memory, and also you can verify whatever program has been stored. So boundary scan helps in not just your monitoring or scanning through all the data which is there inside and every corner of the processor inside, but also it helps in interfacing the memory or updating the memory, upgrading the code, upgrading the operating system. So those kind of things are done by using boundary scan. And these days, this is also connected to Wi-Fi and other stuff, where you can over-the-air programming is also possible for microcontrollers. So there are microcontrollers in ARM and even other companies where you don't need any USB cable to be connected to the computer. You can simply connect it to either Bluetooth or Wi-Fi signals, and then if your integrated development environment, basically the software interface where you are writing your C or assembly code, that is called IDE, integrated development environment. So through IDE, if you connect through Wi-Fi or Bluetooth, some microcontrollers actually get, you can update the code or you can upgrade the firmware of the microcontroller just over the air. That means wireless programming of a microcontroller. So such microcontrollers are present. Those are called wireless SoCs, system on chips. Okay.
Sir, could you explain, like in the last slide, like there were two kinds of arrows, a bold one and a thin one. Could you explain the difference?
Yes. So the bold ones means, so you have multiple lines. Let's say there are 4 lines, 3 to 0. Okay. So 0, 1, 2, 3. So 4 lines means bold lines. And whenever you see the single line with the input or output side direction, so these are single lines. So that means it indicates one connection. Okay. Similarly, for this also there are 4 lines. Actually this is a little mistake in the from the data sheet that I get to see. So there are, but it is actually, you cannot say it's a mistake. It's written as 11. That means 11 lines are present. Same thing wherever you see this bold thing. So that means there are multiple lines. So this is a bus representation. So bold line in embedded system represents a bus representation. That means more than one lines are present. And if you use a single thin line, it is a single wire interface. Okay, so there's a bus interface category, which is a board line, and wire interface category, which is a thin line. Okay, so let's move on. So in the in this particular slide, it is shown that what is there inside the processor part of the processor ARM7 microprocessor. Okay, look at the left hand side part. This is the very core part, or this is called the core of the microprocessor. So core, so Intel Core i7, so Core i9. So what does it mean, core? So the core means the heart of the microprocessor. That means the execution and processing unit for the microprocessor is called as core of a microprocessor. Now, why I'm more talking about microprocessor? Because ARM is actually a microprocessor. So whatever we use in the in the chip form, those are microcontrollers, which is based on this ARM microprocessor. Okay. So the core has basically, let's look at from the somewhere in the middle. So there is a 32-bit ALU. So that means there is a 32. This ARM is a 32-bit processor. And obviously ALU supports multiple instructions, different arithmetic and logic instructions or operations. So those are different circuits present inside ALU. So the ALU circuit is quite large, and they made optimize each and every operation to be very fast and low power. So it is quite a bit of work. I don't know how many engineers worked over it, but it's a very big task. It takes several years to develop each and every microprocessor core, and especially the ALU part is very critical, and it is pretty well developed also these days over several iterations. Now there is something called barrel shifter. So this barrel shifter is nothing but a shift register. It's a specialized shift register. So specialized means it can do left shift, it can do right shift, it can do certain, it can offload also certain operations from the ALU. So it's basically shifts the data, it multiplies or divides by number, like left shift and right shift. If you left shift a number with appending 0 on the right, it is effect, the equivalent effect is multiply by 2, and the opposite thing is multiplied by divide by 2 if we shift right, we're appending the leftmost digit to 0, digital 0. So those kind of things, increment, decrement, some type of shifting, multiplication, simple multiplication, division can be done by using this barrel shifter. So it's a type of ALU which is offloading. Now barrel shifter may not be always functional. It may also act like a transparent path. If there is a mode in this barrel shifter where it can simply bring in whatever is input, it goes to the output without any operation. Essentially, you have seen in 8051, certain instructions are able to do 2 or 3 steps together. Okay, so that's very important to make the code efficient or to make a processor efficient. So in ARM, such operations are even more popular or more frequent, where every instruction will do some other things in the background in order to speed up the overall process. So that is the higher objective. And then there are multipliers. So this is a dedicated multiplier, and this dedicated multiplier is 32 into 8 multiplier. And there is another multiplier within this ALU, which is 32 into 32-bit multiplier. Okay, so that is another multiplier, which is the main multiplier of ALU. But in addition, if you need a smaller multiplication with 8-bit number, with then this extra multiplier is given, and then you can actually exchange the data between two different buses. You can see there are two buses shown over here, at least over here around the ALU. So A bus and B bus. So these are all 32-bit lines which are present inside, and then each of those buses are having various purposes. In addition, you can see the output of ALU is connected to another 32-bit bus. So a single 8-bit bus in 8051 was shared for all these purposes, right? First data, the second data, and also the result data. So in ARM, they thought that everything should be parallel. Let's have more complexity within the chip, but less complexity outside the chip. So that's why they made so many lines, so many 32-bit lines or buses to make it more efficient, such that there is no clash. So whenever A and B buses are carrying data, your ALU can actually update that its data output to some other registers if necessary. And the possibly the most important connection for the towards the output of the ALU is this ALU bus going towards this register bank. Okay, so this register bank, so there is a huge, relatively larger register bank in ARM, and this register bank is actually constitutes of 32-bit registers, and out of that multiple modes are there in ARM processor. And so for each of those modes there are status registers also. In fact, there are 6 modes of operation, so there are 6 status registers, and then obviously there are other supporting registers in those modes. We'll see those modes very soon. And then a program counter is actually a part of this register bank, because see, program counter is a register connected to some up counter. Technically speaking, it's a special function register with an up counter. So this register, this PC register is connected to a counter, and then the output of the program counter should be indicating the instruction being fetched, assuming there is something going on in ALU and something already done in the instruction, this instruction pipelining. I'll come to it. So something has been decoded, which is going on inside this particular block, instruction pipelining and data register. So there are 3 operations, as I said in this slide. Fetch, execute, decode happens in parallel. So while the third instruction comes in execute form, that means the third instruction has entered. The first instruction entered the execute form stage. That means it has entered the ALU. Okay, so execution is happening at the ALU stage for most of the instructions. So ALU is taking care of the first instruction, and the decode, that means the second instruction, is taken care by this pipelining or that instruction register, and the third instruction is the one which is controlled or indicated by program counter. So the program counter is actually taking care of the value for the fetch operation, and the previous instruction is actually handled by this instruction pipeline. So it actually brings the instruction, the second instruction in the pipeline, and the third, the one which came first has entered already this ALU stage. Okay, so look at this. So you are sending address from this address register, which is actually getting controlled by the program counter, and also if this up counter over here. Program counter is actually not a counter anymore in this case. It is just a register output. But if you want to up count it, you have to send it to address incrementer, and then it is an up counting, and then it goes to the through the bus and it comes to the address register, and then the address goes out to the external memory. And once the address goes out, obviously there are data bus, which is I don't know where it is written. So through the data bus, the instruction or the opcode comes in, and it actually, so here is the data bus. Sorry. Yeah, here is the data bus 3120. So through the data bus, once the address is there, is applied to the memory, the data comes in, and then it goes into this pipeline. It enters the pipeline mode, and then obviously after decoding operation, it comes back to this ALU if at all any arithmetic or logic operation is required. Now the point is, execution is mostly done in ALU, but not necessarily always. Why? Because execution could be just moving data from one place to other place. So that moving data doesn't require any arithmetical logic kind of operation. So ALU is actually free for those kind of execute operation. So in that case, you need additional lines. Also, in parallel, so this controller, which is the timing and control unit, equivalent to timing and control unit, as well as decoder here, is connected to the memory or the programming interface. For example, the boundary scan interface or the debugging interface, or even memory firmware upgrade interface like USB or other connections. So all the USB connections are missing over here. So ARM is a processor, USB is a peripheral. Okay, Wi-Fi or USB. So those are all peripherals. So if you need a peripheral, you have to go through some of these lines, interfacing lines, and in certain cases, peripherals also demand this data and address lines to make it to operate correctly. And there is a scan control, which is the boundary scan control. As I said, the boundary scan is to just a copycat everything. It just copies everything. So this boundary scan is such a big circuit, although it's shown as a small block over here. So it's a very big circuit which actually can access every part of this architecture. Like it can scan what is going on in address register, what is going on in incrementer, what is going on in all these SFRs, what is going on in the barrel shifter, or whatever control comes to the barrel shifter from the controller unit. Also, this can basically it can access each and every part of this architecture. So that is the meaning of this. Okay, so this pipeline control, it's a separate block which has been shown because it actually is a very top level control which only handles the code flow. Basically, once how the data or in the opcodes from the memory comes in or goes out. So that is actually controlled by the pipelining. But once the data comes in a given sequence, the instruction decoder will actually take care of the subsequent steps, like what are the steps for decoding, whether to involve ALU barrel shifter multiplier, or you just go to the register bank, do some updation work, or you just stay within the memory to memory data transfer, like a bulk data transfer is requested. In such case, those instruction decoding and execution steps will be followed over here. So you can think that this pipelining stage is or this instruction pipelining and thumb instruction controller. This is a very big boss. This is the CEO of your microprocessor. Okay, and this instruction decoder and logic control, these are managing directors or vice presidents of your processor, and these are top level officers who are actually present working on the shop floor for the ALU multiplier and so on. So this is an analogy that I am just trying to tell you. Okay, so this processor architecture, again, you don't have to learn by heart. You can always refer back to such diagrams. But more importantly, you should understand what I am saying. Okay, you should understand and interpret. You should be able to connect. So that is important. Okay, you should be able to reason my statements. So everything is going by logic. And while that logic, what is the objective behind the logic? The objective is to speed up the process of execution, to reduce power consumption, and also to make the overall system efficient and powerful. So those are the objectives. And what is the logic? So how the data will flow, what should be the sequence of operation, why there are multiple buses to make it parallel, and obviously why there are scanning control, why there are basically logic control, why there is a pipelining control. So pipelining is to just make sure that everything happens in parallel. Instruction decoding and logic is just to have the for a given instruction, what are the sequence of operation that you should look at, and after decoding that instruction, obviously. And the scan control is to have a copy of each and everything without disturbing the normal operation. Okay, and all these lines which are actually for logic control. So this logic control signals, some of this goes to the peripherals, some of this goes within the core of the microprocessor, and so on. Okay, so that is the overall objective and the logic or the reasons behind such a diagram. Now, the ARM company, they come up with a revised version of this particular diagram with every version that they are producing or selling. So ARM 7 is a very commonly used microcontroller series, which is being manufactured by many companies. We'll see one of them from NXP. NXP is a Philips company. It's a Philips subsidiary for semiconductors. So NXP is a very big company who fabricate the microcontroller chips around ARM 7. So we'll look at them basically. So beyond before going to those kind of detailed slide-ish details, so let me show you some interesting thing from the datasheet. Okay. So I told you that we are going to look at NXP processor. NXP is a subsidiary of Philips, and we will look at NXP processor LPC series. So LPC is I don't know what is the full form of this because I never came across in their datasheets or user manuals. Possibly low power controller, possibly, or but I am not sure, to be very frank. Okay, so low power controller, so that might be the full form of this, but again it's not documented, so I cannot tell you for sure. Anyways, whatever might be that, so LPC 21XX series, so that means 2131, 2132, and so on up to 2138. So these are this is a series of microcontrollers under the ARM7 category, which are manufactured by this Philips. And we'll see to the later about this I2c bus. I2c is integrated circuit bus. It is a brother of UART, you can say. So it's a synchronous serial port. UART was asynchronous serial port we had seen. So this I2c was originally developed by Philips, and that's why they are advertising possibly here. But let's leave that out for later on. So this LPC series will mainly look at LPC2138 microcontroller, and this microcontroller is quite powerful microcontroller, and it represents some of the most of the basic features that ARM7 offers. And look at the terms that they are saying: single chip 16/32, because thumb mode and full ARM mode are supported microcontrollers, because they have included memory and peripherals. That's why it is microcontroller. And they have 32 or all those values up to 512 kilobytes of ISP or IAP flash with 10-bit ADC DAC. So now let's look at from simple to relatively complex. ADC and DAC, you know, analog to digital converter, and then DAC is digital to analog converter. So that means this microcontrollers not just handle digital data, it has some interfacing for analog signals. Okay, so you can bring in analog signal to the microcontroller, convert that into digital, and do some processing, and again convert that back to analog if necessary. Okay, so that's why this is a mixed signal microcontroller. So that's why we call this LPC, or many other modern microcontrollers are mixed signal typical. ADCs and DACs are present. ADC is very common. Almost every microcontroller offers ADC these days, but DAC is not as common as ADC. So DAC is relatively less common. Now, let's look at this term: ISP and IAP flash. ISP means in circuit or in system programmable. If you remember 8089S51 that we had studied earlier, S51 means in circuit or in system programming supported. Okay, and IAP means in application programming. So in system programming, in application programming flash. So flash memory typically requires higher voltage for programming, for writing into the flash. Suppose you are updating your firmware, so flash requires some higher voltage, and that higher voltage is automatically supplied within this chip. So there is a boost converter within LPC, and then that actually helps to program the code memories or lookup tables or permanent data into the flash memory. And this 3.1 is having 32 kilobytes of flash, 3.2 is having 64 kilobytes, and so on. So 38 LPC2138 is having 512, that is half M bytes of flash within this, and every location is in system or in application programmable. Okay. So you can read through the descriptions. I will go through some of the features and benefits. So this is very important: features and benefits. Okay, 1 minute. Okay. So some of the features of this are, so let's look at the key features first, then we'll look at those enhanced ones later on. So key features of for this LPC2138 series microcontrollers. So it offers 32 16-bit ARM7 TDMI. We have seen what does that mean. Thumb mode, debug operation, multiplier, and in-system programming, and then synchronous mode for co-processing. So this is the meaning of ARM and version 7 for this ARM. And it is available in two packages. So these are the physical packages. Like for 8051, we had seen DIP package, dual inline, so two-sided pins for those 40-pin IC that we had seen. For ARM7, this particular 213X, it offers LQFP. LQFP means low profile quadrature flat package, or quadrature plastic flat package. Okay, so this is having 64 pins over here. So low profile quad flat pack. This is one of the surface mount packages that is offered. And then there is another one, high voltage quadrature flat no lead package of 64 pins. So high voltage quadrature flat no lead. That means there are no pins coming out of it. Rather, there is little metal dots which are available on the package, and this is very small sized package. This QFN is quite small size package. LQFP is also quite small but relatively larger, and both of these are extremely smaller in size as compared to your 8051. So 8051, so it was in inches. The length of or height of the chip was in inches. If you come from pin number 1 to 20, so the length is quite is more than, I think, 2 inch, whereas everything over here is just few millimeters. So obviously you can convert. So we'll see that. So this QFN one is 9 mm by 9 mm, and this QFP one is, I think, 12 mm by 12 mm. So it's just that small. Whereas the other for 8051, it was about 50 mm by some 20 mm kind of thing. So it's drastically small in size. That's one thing. There are different sizes of RAM in this LPC series. In that LPC series, you can see 8 or 16 or 32 kilobytes of on-chip SRAM is present. So SRAM is the one that is forgets the data if you power off, and there are on-chip flash program memory that we discussed. And look at this 128-bit wide interface accelerator. Okay, so that means 128-bit wide. How it is possible? It is possible because of those multiple buses that we discussed in the PPT sometime back. Okay, so there are 4 different 32-bit buses which are present inside this ARM7, and those 32 bits, basically 4 into 32 is 64. Basically that is 128 bits. So this 128 bits wide buses are split into 4 buses, obviously helps in fast operation at 60 megahertz, so that at sustained speed of 60 megahertz it can actually run all 4 buses simultaneously, given you have that requirement in your code or instruction. So if that happens, all 128 bits will operate simultaneously at 60 megahertz. So it gives exceptionally high performance as compared to 8051, uncomparably high. So so no comparison at all. So then in system and in application programming, so on-chip bootloader software. So what is this bootloader software? Bootloader software is a little piece of code that we cannot change. So this is a hard coded. So there is a read-only memory part in this microcontroller, which is stored by the manufacturer during its fabrication process. And that part, little code, if you start up the processor, it will always be it will always come into action. And this on-chip bootloading means once you turn up the processor, it will start executing the bootloader code, not your own code. In 8051, whatever code we write at org00 or something, so that gets executed. But in in this ARM7, it's not like that. So after power up, it will only execute the booting code, and that booting code is programmed by the company, not us. And what does it do? What it does is the following. So the bootloader code will first see what is the hardware condition around the chip. Let's say you have powered on, obviously then only the bootloader will be executed. Now, after power on, what is the state of the reset? What is the memory that is connected to your chip? So all sorts of checkup, basically startup check or basically supervisory check will be done, and it will also see whether you want to update the flash memory or not, you want to write, so whether it's the first time flash uploading or not. So those kind of checks will be done. And if you are saying through the IO lines that I want to program the flash with my own code, then it will actually facilitate, it will turn on the buses for accessing the flash, generate the higher voltage for programming, and then it will help us to execute or store the flash. Suppose on the other hand, we have already uploaded the flash, second time we are doing that, starting it in the processor. So the bootloader will see that, okay, no, flash is already present and it is already programmed, possibly because there are some boot sector information which gives such data to this bootloader software, and the bootloader will actually take you to the normal execution mode. Okay, you have some data or code in your flash, let's execute that program. And now the bootloader will take a side stage. Now the main program that you had written possibly will be executed. So that's the part of bootloader, but you cannot change. You can write wrong code in on your flash, which may completely hang your processor, but afterwards, if you restart, the bootloader will actually take you out of such situation. You can reprogram the flash from scratch or properly second time or next time. So up to certain number of times, that we'll see how many. And then single flash sector or full chip erase. So what is a sector? So in the memory, there is something called sector, there is something called page, and there is something called basically the full space or full memory area. So sector is nothing but is a group of locations in a flash. So if you go deeper into the flash memory technology, so you can go into at least two ways. One is the physics part and the fabrication part. I'm combining them together, although they are different in general. But physics and fabrication of flash is one thing, and another side, how to use it in our microcontrollers. So that is much more simpler way. So how we use it in our microcontrollers. So the flash memory can be erased in sectors or pages. Means you can only erase a group of memories. You cannot delete one byte information from a flash memory or one word information. You have to delete in a group, let's say 256 bytes or 512 bytes. So a minimum number of memory locations are grouped together, and that is called sector, or even page also, some people call it page of a memory. It's like in one page of your notebook, there are multiple lines. You can write many things, but let's say you want to delete whatever you have written, you are not allowed to scratch one line, rather you have to scratch out the entire page. It's like that. So the flash memory should be erased in a group, in a sector. Okay, well, but for programming you can do it byte by byte, but for erasing it is in a group. So that's what single flash sector or erase or full chip erase. So that means you can erase in a group or enter chip at one go in within certain time, like 400 milliseconds and so on, and programming of 256 bytes in 1 millisecond. That indicates the sector size is 256 bytes. Okay, so that means you have to delete 256 bytes in a given shot, and while programming also, so you have to you can program up to this 256 bytes within 1 millisecond. That means you can program byte by byte after erasing, one byte at a time, or 4 bytes or 2 bytes at a time, but up to 256 bytes within 1 millisecond. So that means if you write a code which is more than 256 bytes, you are actually storing that code in more than one sectors. Okay, try to understand what I'm telling. This is a concept that you have to grasp. That once you are writing a code, let's say your code is 300 lines, or it takes 300 bytes, rather lines, 300 bytes. So what it will do, it will go to the first sector, it will store 256 bytes over there, and remaining bytes from 300 will be stored in the second sector. Now, if you want to delete your code and update your firmware, then you have to delete or erase both the sectors where you had stored or splitted your code for the 300 byte memory that it was occupied. Okay, so this is one important concept, which is an embedded system concept. And now the question is why we need this kind of sector kind of thing. Why it is not a continuous memory? Okay, so why it is not continuous memory? Because so while there are multiple reasons actually. So one such reason is that while the manufacturer fabricates, they fabricate in cells. If you remember the VLSI lab analog, we in cadence part we were talking about cell view and new cell design. So cell design means what? So you are designing a schematic within a cell. Okay, so it's a terminology. So that means if while developers are designing this kind of microcontrollers, so they also design cells. So they use cadence and they use cell level development. That means they develop, let's say, 256 bytes of flash memory within a given cell. Now their big boss comes and say that, okay, I need in one microcontroller I need 32 kilobyte, another one I need 16 or whatever this flash memory in this case. So I need 32, 64, 128, 256 and 512. These are the variants I am interested in. There, let's say big boss is saying. So what the designers will do, they will take the cell and then they will repeat it until it is 32 kilobytes. They will repeat it until it is 64 kilobytes. So that means they will invite and merge more number of cells as you go up in the memory size. Okay, so this is a scalable design approach. Means, so you have a small unit, so you have one brick and you just purchase 1,000 brick, you make one room, and then you need another person comes next, he says that, okay, I want a bigger room. So obviously you add more bricks and you make a bigger house out of that. So same thing is over here. So the memory segment or sector is like a brick. Okay, it has 256 brick kind of location, and then you keep on having a multiple of this sector to make a larger memory. So that is one reason. Another reason is that in flash, so in order to reduce the number of lines that goes into the runs into the transistors inside the flash memory, so they wanted to reduce the number of connections for each and every transistor which are used for every location, bit location. So to reduce the number of connections, they actually make certain things in parallel. That means one connection for the high voltage part of flash programming goes to the, let's say, 256 bytes at a go. So it saves a lot of on-chip real estate or space. So that is another reason. Okay. Uh, and the second and the next point is embedded ICE. ICE is in-circuit emulation, and RT is real-time. In-circuit real-time emulation actually means in real-time emulation in the sense means whenever you are running a code, so it is the processor is running at 60 megahertz. Okay, at 60 megahertz. Assume it's the maximum specified speed. Although I have personally used it up to 100 megahertz. I've personally checked it. But at 100 megahertz, the performance is not guaranteed. So it's not recommended. 60 is guaranteed. So at 60 megahertz, there are many registers, so many things inside the microcontroller, the microprocessor of ARM7 is going on, and through the boundary scan, actually you can actually do some emulation or sniffing action, right? So you are copying everything to the outside. So in circuit emulation and real time, that means if you want to update any special function register, not by your code, just by your debugger interface. So you have to understand that if you can write your code and then upload your code or download your code to your microcontroller flash memory. So that is one way of doing it, the thing. But while the processor is executing a code, you can actually apply a breakpoint. And breakpoint is nothing but you stopping or pausing the processor and not allowing it to go to the next instruction. So breakpoints are possible at any location within the memory space. Just a minute, I'll drink some water. Okay, sorry. So the breakpoints can be applied anywhere within your code. Now, after applying breakpoint, suppose I want to update some register. Suppose my main code must be doing something with a given register. Take any register, let's say program counter or anything. And then I wanted to change the value. Suppose I found a mistake and I want to play around with the value without changing the main code. So I don't want to download my entire firmware into the flash. Rather, I want to just change and try out some other coefficient or some value within a register. So what I'll do, I will apply a specialized hardware interface. It's like an USB cable with some specialized hardware, which gets connected to the microcontroller chip. And then in real time, I say that, OK, now I don't need this PC value. I change it to something else. So I can write those value on my software interface, like Arduino interface. Arduino is a very simple interface for this ARM. It is relatively more complex in general for ICE interface, but it is not very difficult also. So I can write any value to that target register, and in real time, I can stop the microcontroller or pause the microcontroller through this ICE interface, and then I can update the value to that register and then run it again at my will. So I can remove the breakpoint or just go beyond the breakpoint and run normally. So that is ICE RT, the in-circuit emulation. So emulation means it's equivalent to simulation, right? You have done LT-SPICE simulation. So LT-SPICE simulation means it's completely virtual. So that means circuits are not physically present. It's all there in the virtual domain on your schematic on your computer. But in emulation is one step closer to real thing where the hardware is also involved. So emulation is a process where you actually run the hardware at your own control, but you are actually holding strings at every point. That means you are able to manipulate how the hardware will run. It is not a free flowing run. Actually, you can put it in free flow mode, that means normal execution mode, but you can actually stop it and then do some changes and then check what is going to happen. And then you are also measuring the effect of your change. So due to whatever you have emulated. So suppose you have emulated with certain value of in the special function registers, and then after updating that value, you want to find out what is the effect of such change. So that is embedded trace interface. Okay, so trace interface is nothing but it is again done through the scanning method, the boundary scan method that we described. So the tracing is about what is the behavior of the processor, what is the effect of those change that you have done through emulation process. So that is you want to trace, you want to measure back through the hardware lines that how the hardware is behaving due to those hardware changes that you had given. Hardware changes means either some value change or some connectivity change, which is possible in certain ARM processors. Although in this processor, you don't change the connectivity, you can only change the value through emulation process. But there are other processors where you can even change connectivity of the hardwares to some extent. And this is called real-time debugging operation. Okay, so real-time debugging is very important because for developing very complex, time-critical or non-time critical, high-performance embedded systems, you need this kind of RT debugging. And RT debugging is possible is a combination of boundary scan, which is the embedded trace, and in-circuit emulation process in real time. Okay, so while you can do it in real time, that means during runtime. Okay, real time or runtime. And such thing is done by using a software called Real Monitor. So Real Monitor is a software. We will not cover this in the course, but this is a software provided by ARM, and we have to license that. I don't have the license in my lab, or I don't know anyone having in IIT. But this Real Monitor is a software which is actually compatible to those boundary scan and debugging lines, and then it actually controls the operation. It helps you to update any hardware block inside and then also measure it back, the effect of that. And that's too, it is possible at a very high speed at near 60 megahertz. So high speed tracing of instruction execution. That means instructions are executed at 60 million times a second. Okay, 60 megahertz. But this real monitor will do all sorts of high-speed transactions or data exchange or readout from the chip, and then it can give you the complete map of the instruction execution. That means how your jump instructions behaved, how your call instruction behaved, how the interrupts were serviced, how the SFRs, what are the values of SFRs, or how they got updated, how the status got updated, everything. It gives a huge data, which is a snapshot of the operation through the trace and emulation operation. So this is very, very powerful thing, feature, which is there in ARM processors. And this feature may or may not be enabled by the companies who are manufacturing the chips. So like NXP in this case has enabled it, but let's say if you are using 8-pin little ARM microcontroller from any company, even NXP may not be supporting this RT, ICE and trace. Okay, so I think this is a new concept. That was a new concept. That's why I was spending so much time over there. Let's rush through a bit, which are pretty similar and easy to understand. So this LPC has 8-channel, let's say 2 8-channel or 1 8-channel ADC, 10-bit ADC. So that means 10-bit is the resolution of analog to digital converter, and 8 channels means there is a multiplexer. So there is one 10-bit ADC which is multiplexed from 8 input channels. That means 8 inputs, any one of the 8 can be connected to the ADC at a time. And there are two 10-bit ADC or one 10-bit ADC with such multiplexers. Okay, so that means up to 16 analog inputs are possible if it is 2 8-channel. So 2 into 8, that means there are 2 ADCs. Each ADC is having 8-channel multiplexer, and then combined together it's a 16 analog inputs. And this is the conversion time, so it takes about 2.4 microseconds per channel to do the conversion, and you have to multiply that into 16 or 8 based on how many multiplexer channels you are using. And it's not necessary you have to use all of them. You can use one of them also. You can use any value up to 8 per ADC, and maximum is 16. Then there is a 10-bit D2A converter, which so that means you can generate a sound signal or some sort of sine wave signal, or function generator operation can be done by using this DAC. So this is important. Why we need DAC? We can use it to bias external amplifiers or any external circuits, or you can drive the LEDs power. Or you cannot drive that directly, although it can generate you the voltage, which is under the control of the microcontroller inside. And then there are timers. There are 32-bit timers or external event counters. So you have seen timer / counters. So here they are changing it to event counters / timers. And each of them is 32 bits wide. That means there is a wider range of time counting or up or down counting. Both are present over here. Unlike 8051, up and down counting are present here. And there are different capture modes. So this capture mode was absent in 8051. So capture mode means you can actually start from any count. So it's not necessary you have to come to 0 or all ones. You don't have to go to the extreme limits actually. So all zeros or all ones in this 32 bits. You can start anywhere and also stop anywhere. That means it will capture a certain number of counts, and then it will stop and generate interrupts to the microcontroller. That means you can initialize the timer or counter anywhere, and you can actually stop it also anywhere by assigning where to stop, and that is called a capture operation. So once the particular value is present within the timer, it can stop and capture, and it can just indicate the main processor that okay, I've captured a particular value that you wanted to find. In addition, there are other functions, auxiliary or important functions of this timer, which is pulse width modulation. So PWM is very important for motor control application like speed control of railway motors, or LED light intensity control, or even fan motor speed control and so on. So there are lots of application of this PWM where the pulse width modulation is done, where you can set the duty cycle, you can set the counting operation or timer operation. You can set a time period basically, and you can set a duty cycle, and it will keep on generating a clock signal with that duty cycle. You can change the duty cycle within minimum and maximum limits, and there are up to 6 outputs for those duty cycles. So that means you can think there are up to 6 motors can be driven from here, or up to 6 LED channels can be driven, or up to different, you can control the e-bike or electric vehicle control. So suppose you have a 4-wheeler SUV, electric SUV, for example, which are coming. So you can actually use this PWM signal. In fact, PWM is used in engine control unit, ECU, in the cars like SUVs and other cars. There is a Watchdog timer. So Watchdog is another special timer which is present. Watchdog is a type of a specialized timer which gives a periodic bark. It's like if you're keeping a dog at your house, it'll bark with some time in between, right? And that timing may be different at times. But Watchdog is a type of timer which gives a periodic interrupt signal to the microcontroller. So that is the meaning. So the Watchdog timer is a periodic timer which automatically counts if you enable it, and it gives a periodic interrupt signal. And what is the advantage of this? Why you need this kind of disturbing timer signal? Because it helps you in the operating system like task. So in operating system, so this microcontroller ARM is used for is designed with operating system in mind, like RTOS, real-time operating system. So we'll look at some features of RTOS later on. So RTOS means real-time operating system, which are used in typically in embedded systems, where you need to serve multiple real-time operations. Suppose I want to apply 16 sensors to these 16 ADC channels. Assume I'm measuring in an industry, in a company, I'm measuring air quality, temperature, humidity, light intensity, some speed of motors, how many people going in or coming out. So all sorts of signals can be measured by using different sensors and connected to ADC or to directly digital input output channels. And while doing that, I want to do all of them without error. Okay, so I don't want to miss time whenever there is a change in number of people who are entering or leaving the campus or door, or even the temperature changes. I should also update temperature simultaneously. So I can do one thing in code. I can always run the processor at high frequency like 60 megahertz, and then keep on doing all the things in our code. We can manage all those things in our code. So that's possible, but that's not very efficient. So to make it efficient, what if someone is telling you, okay, why don't you look at the next task in hand? After, let's say, every millisecond or two, or whatever time after which this watchdog is activated, it generates an interrupt and it tells, why don't you scan through the next sensor channel? So it goes to, it'll keep on doing scanning within 16 milliseconds, for example. It will scan through all 16 channels, and the watchdog is periodically reminding the processor. It's sort of assistant who is reminding the main processor that you have to do the next task. You don't get bogged down with only one course or one subject. So it's like that. You have to watch out for the other subjects and complete assignments for the other subjects. So it's a periodic interruption for a good cause. Then there is a low power RTC, which is real-time clock. You can maintain seconds, hour, minute. So the stopwatch function in your mobile phone is done by using this RTC block inside the ARM processor. Okay, all you have to do initialize when to start, what is, whether it is a simple time counter or it is a stop counter or stopwatch. So those modes are all featured over here in RTC block. And RTC block requires a dedicated crystal or clock source, okay, which is 32.768 kilohertz. It's not exactly 32, it's 32.768 kilohertz. And that's a very standard crystal frequency used in every watch that we use, every watch almost. every wall clock, every mobile phone, every laptop, every device that we use wherever which is related to clock signal, it is 32.768 kilohertz signal, and it is one of the reasons why 768. Then there is a calculation behind, and you can read through. And this RTC clock source is different than the 60 megahertz clock source that we have seen. So that means ARM processor requires at least 2 crystals to be connected. One for dedicated for RTC, and this is a very high accuracy, low frequency clock, and the other one is also highly accurate but high frequency clock for the main processor application. And then there are multiple serial communication. Now you will get lots of features over here for the serial communication. There are 4 different types of serial communication here. So first is UART, Universal Asynchronous Receiver Transmitter, and 16C550 represents one of the obsolete chips, which is obviously here it's not to downgrade the capability of this chip, of this ARM chip, but it is just to say that it supports traditional way of UART, and the traditional way you have already learned in 8051. So that's the traditional way. And there was a chip before this microcontrollers came, which was 16C550. Now it is not available, and all microcontrollers are having this feature integrated. So there is no specialty about this number. Then fast I2c buses. So this I2c and other protocols are the serial communication protocols. Inter-integrated circuit bus, which runs up to 400 kilobits per second, and SPI serial peripheral interface, which was developed by Motorola. I2c was developed by Philips, and UART was by Hewlett Packard. So SPI was SPI is serial peripheral interface. This is another synchronous serial port. That means there is a clock signal here. Also, there is a clock signal here. As well, there is a synchronous serial port, which is a modified version of SPI. It was developed by National Semiconductor, which has been merged with Texas Instruments these days. So synchronous serial port SSP interface, which is actually slightly different than SPI, more or less same. It has one sync signal, extra signal that you'll see separately. So this is very infrequently used these days. Very commonly used are SPI, I2c, and UART. These 3 are very, very common even today, with even the most advanced microprocessors and controllers. So, and it also offers buffering along with the serial communication. That means if you remember SBUF for TXD and RXD, so the register in 8051 that was storing 8-bit data for transmission or reception. So similar thing is there in in ARM7, but where the buffering is much more well managed. You will see how it is managed. So there are some hidden registers where buffering happens. That means if there are more than 1 byte comes at a time, the processor will be able to handle them without damage of the first data. Okay, so that is important. And then there are variable data length capabilities because it utilizes RAM space in one of the modes where you can have more than 1 bytes of data, and such buffering, that means the buffer size is no more than 1 bytes. So that is the meaning over here, variable data length. Now coming to very important thing, vectored interrupt controller. So although from this page I cannot describe you much, you have to look at some diagrams for this. So here the controller, the microcontroller NXP LPC is supporting very powerful interrupt set, and this interrupt comes from the original interrupt capability of the ARM7 architecture. Vectored means basically, so in 8051 we have seen that different interrupts were giving different vector location. That means start location for the memory space. So such vectored, that's called actually vectored memory location or vectored interrupt. Okay, that means every interrupt is having a dedicated memory address in the code memory from where it should start executing, and that is called as vectored memory. That means it is predefined, and the interrupt controller over here is actually much more powerful because it is reconfigurable priorities and vector addresses. In fact, you can determine which address it should follow for certain interrupts, not all. for certain interrupt sources, you can actually determine the address values, which was not at all possible in 8051. And then priorities can be set over here. So that means which interrupt should be serviced first. Like interrupts could be there with ADC, interrupt could be there with DAC, timers, counters, RTC, whatever we have covered, I2c, SPI, UART, everything can have its own interrupts sources. And if all of them are more than one gives interrupt or generates interrupt at a time, you can set their priorities, you can arrange their priorities in this particular microcontroller. And this microcontroller supports, so there are up to 47 GPIO ports, so general purpose input output port pins, and all of them are heavily multiplexed, and then obviously, as we discussed, the packages: low profile quad flat pack and high voltage quadrature flat no lead package. Okay, so you don't remember this kind of names, so you can always look back and refer. So if you use these packages very frequently, it will automatically come to your mind. You don't have to remember separately. You don't have to stress yourself. Okay, then there are up to 9 level and or age sensitive external interrupts. So in 8051, there are only 2 interrupt sources, INT0 and INT1, both were bar. But here it's up to 9, and here you can also select not just age or level. Level means whether 1 means interrupt or 0 means interrupt. So that is the level sensitive interrupt. So you can set all those 9 pins among either high level interrupt or low level interrupt. And then there are age interrupt, that means low to high transition makes interrupt or high to low transition makes interrupt. So those features of those interrupt 9 interrupt sources, external pins, which are merged or multiplexed with these IO pins, can be set by means of SFRs. So that means as you see more and more features, you can expect more and more special function registers, which allows you to do all those features. So you have to always see that more features that it supports, more flexibility the microcontroller is featuring, obviously more number of SFR bits or bytes or words you have to configure. 16 MHz, 100 maximum CPU speed with on-chip programmable phase lock loop. Okay, with settling time of 100 microseconds. Okay, so now this is very interesting. So although the CPU works at 60 megahertz, the crystal that you need to use may not go up to this frequency. Suppose you can use 1 megahertz crystal and still achieve, let's say, 60 megahertz signal for the CPU. What is the reason behind? The crystal, if you connect a high frequency crystal, it requires physical pins to be connected to the microcontroller. And physical pin connection means physical wire present or some conductive path that offers parasitic capacitance. And the moment you have capacitance, and obviously some wire resistance will be there, it forms a filter. So it becomes a low pass filter. So any physical connection in this world for the electrical, any physical electrical connection, I mean, offers some sort of parasitic resistance and parasitic capacitance. And as a result, it forms a time constant, and depends on how their resistors and capacitors are connected, it becomes either high pass or low pass. So in case of this kind of operation like this chips, it forms a low pass, and as a result, your 60 megahertz clock will look like a sine wave if you apply from outside. If you connect a crystal from outside, at least it will become a distorted sine and a combination of distorted sine and distorted square. So it will never become a smooth rectangular or square wave signal because of the time constant gets associated due to the parasitics. Now, so what is the alternate reason or alternate method? You can use a crystal which is 1 megahertz to 30 megahertz. Okay. So you can use this crystal, and if you use an external oscillator, so you can use up to 50 megahertz, but that is not very recommended way. Okay, so typically we use 1 to 30 megahertz and multiply this thing, this frequency, by using on-chip phase lock loop. If you remember phase lock loop, have you studied phase lock loop? If you have studied phase lock loop in other subjects, you'll see that if you can use a divide by n counter in the feedback path of PLL. Okay, so PLL is a phase lock loop, and in the PLL has a feedback, and in the feedback path, if you use a divide by n counter, then the output of the final output, which is the output of the voltage control oscillator of PLL, if you remember and recall the block diagram, VCO output is the final output of PLL, which gets multiplied by that n factor. So if you use a divide by n in the feedback, the overall frequency is the multiplied by n. So input frequency gets multiplied by n. So that means if you use divide by 2 with this 30 megahertz, so the 30 megahertz input crystal frequency will get converted into 60 megahertz, and so on. If you use divide by 60 with 1 megahertz, it will again come to 60 megahertz. So this technique is very important, and it is super important in each and every desktop computers also. So while we say that for example, I'm using an i7 processor in my laptop, which can go with turbo boost of 5 gigahertz. Okay, so this 5 gigahertz crystal is never used. So typically some megahertz crystal like 100 megahertz maybe they are inside my laptop, and then that 100 megahertz can be used along with PLL, or there is another one FLL, which is frequency lock loop. So I'm not talking about this. So PLL one is very simple, and you simply apply that 100 megahertz to the input of PLL, apply divide by n in the feedback path, and the output will be multiplied by n. So that 100 megahertz into n will be the output. So this helps in reduced parasitics, because that multiplication is happening on chip, and due to on chip operation there is less parasitic, and less parasitic means there is less effect of low pass action and time constant. As a result, your clock will be much cleaner clock. That means more like a clean clock signal, but it is never 100% clean. There will be some noise, but reduced, significantly reduced. Okay, so this concept of this PLL and this frequency of oscillator is another important point, which is there in all ARM processors, almost all ARM processors. So everywhere we connect a lower frequency crystal from outside, and then multiply that with some circuitry inside and make it higher frequency signal for a CPU. There are lots of power modes, power saving modes like sleep, idle, power down, and all those things. And then there are individual enable disable for every peripheral. So whatever timer, ADC, DAC, everyone is connected with a switch inside. Okay, so in 8051 you cannot turn off the timer. You can either use it or don't use it. That is enough. Different. Enable it or don't disable it. But here you can power off the timer. In fact, if you check the supply current going inside the chip while enabling and disabling the peripherals like this UART, I2c, so you will see change in power consumption or the change in current that is coming through the VDD line. And then there are peripheral clock scaling. That means you can set, you have the internal clock of 60 megahertz, for example, for the CPU. But for peripherals, typically we don't use such a high frequency clock. We divide it, as we had seen with 8051 serial code. So we divide that, and then that division of clock signal is called clock scaling. So for peripherals, each and every peripheral, you can individually scale the clock frequencies. That is, you can individually change the clock frequency, which are often below the maximum CPU's frequency, and then apply it separately. So that means what? What is the meaning behind this clock scaling? We can set or control the dynamic power consumption. Remember, dynamic power consumption in digital circuits is P dynamic equal to C VDD square F. Okay, so VDD square F. So F is proportional to directly proportional to the power consumption, dynamic power consumption. So if you scale down to lower frequency, your dynamic power will reduce for the given peripheral. Obviously, speed of operation of the peripheral is another constant. You cannot do that scaling indefinitely. So you have to take a right choice of how much scaling is important or applicable while running a peripheral at a particular baud rate or speed of operation. Okay, so you have to make a judicious decision while selecting these parameters. So this is mainly used for power optimization. purpose as written. And then there are different ways to wake up the processor. Suppose you're putting the processor in idle or sleep mode or power down. There could be different modes. It can be done through external interrupt or different your software in based waking up is possible. And this is something called BOD, which is called brown out detection. Brown out detection. BOD means what? Brownout means if there is an intermittent power failure. Suppose you have applied a power supply and then there is an intermittent power failure. Let's say there is a little loose contact somewhere or so. So your code should not run, or misbehave. Suppose if you drop your phone, what happens? Your battery in older phones, at least, we are using detachable batteries. That means battery was removable. So the connectors were there. The connectors can malfunction while the phone is dropped. So even after dropping, so for minor drops, we don't get to see any problem because there is a BOD circuit inside your processor, inside your phones, where so brownout detection actually detects if there is intermittent power failure. Let's say for a few milliseconds the power is off or reduced to some voltage beyond limit, and then it comes back again. So that is called BOD detection. So if such brownout condition happens, it detects automatically and it actually makes sure the processor wakes up properly through the bootloading code sequence. Okay, so the bootloader that we discussed. So that is also, that has certain precautionary code for this BOD. So this BOD is actually a combination of the hardware voltage sensing and the bootloading code that actually also plays a role in this BOD process. And the single supply chip with power on reset, POR is power on reset, and BOD is brownout detection. So single supply, so that means whenever you recover from power on after, or you recover from brownout condition, so the single supply chip or this particular chip will start running within this range, typically 3 volt to 3.6 volts. So there are variants where the same design could be, the same ARM7 could be 1.8 volt, the same ARM7 could be 1 volt also device, depends which technology it adopts. So this ARM7 LPC chip is using 350 nanometer technology, and that is why it supports this 3.3 volt. So nominal voltage is 3.3 volt supply and typically up to 3.6. If you apply 4, your processor will go bad. It will never come back. But the point is, look at this controversial statement. 5 volt tolerant IOs, how it is possible? So in if you look at PDKs, such as in Cadence, obviously in LT Spice it is not possible. You'll find within a given technology, so there are some high voltage tolerant transistors, like these are transistors having thicker gate oxide, okay, as compared to normal thin gate transistors. So as we scale down in size, so there are so without changing the length of the transistor, we can just increase the gate dielectric width such that it can withstand higher input voltage, and higher input voltage means higher electric field intensity. Okay, so the higher electric field intensity due to 5 volt is tolerant for the only for the IO pins, not inside. So if you apply 4 volt over here as a power supply, the CPU will go bad. The IOs will stay okay, but if CPU is bad inside your chip, that means your chip is partially damaged, and partially means actually it is useless. Okay, so I'll take attendance. So I'll just show you some last few before packing up. Just I'll have just a few things. So look at the packages. HVQFN64. So it is just look at this dimension D and E. So this is a square kind of chip, actually octagonal. So D is just 9 millimeters. Okay, so it is, and E is also 9 millimeters. So it is just 9 mm by 9 mm chip. It's a very small form factor, where it is called quad flat no lead package. So what is the meaning of this no lead? So it doesn't have any pin protruding out. It has the body of the chip, and the body is metallized. Basically, some part is having metal contact, and you have to solder your chip onto PCB by using those metal contacts. So there is no pin coming out. So this is quad flat no lead package. and there is another package called quadrature flat plastic package. So this package is having small pins, right? So these are the small pins which are coming out. There are 64 of them, and the 64 pins are also having this kind of kind of wiggle shape, and the size of the chip is, let's look at it, HE and HD. So HE is just 12 millimeter, and HE and HD both are 12 millimeters. You can see this is a 12 mm by 12 mm chip. It's pretty, it's not very easy to solder, but it's not too difficult also. So because these pins are very close by, here the pitch between the pin is small e, which is small e is 0.5 mm. So 0.5 mm is the center to center. But if you look at the edge from this pin, the edge of this, so it is actually less than 0.5 mm. Yeah. So I'll take attendance and then I'll back off. Sorry.